Hi, this is the second free response question on the AP Physics C extra credit videos. So here we're given a pretty complex, pretty involved problem, so make sure you really understand it before we get started. You need to know some physics facts. Kinematics formula, change in x equals v naught plus 1/2 at squared. Our energy formulas, conservation of energy, energy conserved when no work done by external forces. Kinetic energy is 1/2 mv squared, and potential energy is mass times gravity times height. Students, so the first thing we're asked to do is draw a line best fit. Starts out really easy. Looks like it'd be something like that. And then 250, if this is 300, 250 would be about here. And that looks like it'd be about 33 meters. Okay. Then we're asked, how many seconds after leaving the cup will the projectile strike the ground? Well, we're going to use our kinematics. And we know that our height, our change in y, or I use y because it's in the vertical direction, is 12 plus 3, so 15, equals, and our v naught starts from rest, so that goes to 0, plus half at squared. And our A is just going to be gravity because it's vertical. So 1/2 times 10 is 5 t squared. T squared equals 3, and then using our calculators we find t is 1.73 seconds. All right, not too bad so far. Derive the equation that describes the gravitational potential energy of the system relative to the ground in the position shown in figure 1. Assume the mass in the counterweight bucket is m. All right. So we need to calculate the gravitational potential energy of the bucket and of the projectile, sum them, and then that's going to be our formula. So I'll say UB, that's just going to be m times our gravity of 10 times our h of 3. That's going to be 30m. And r of the projectile, it's given that its mass is 10, times our gravity constant, which we're using 10 for. You can use 10 or 9.8 or 9.8.1. I always use 10 because it's easier calculations, but do as you please. So our potential energy of the system, I'll say use 30m plus 300. All right. Well, now we can move on to number 3. Derive the equation for the velocity of the projectile as it leaves the cup. So now we're going to need to use our conservation of energy formula. And at the start, we know all we have is potential energy. And then at the end, we have our final potential, and we have our kinetic energy. So we just calculated our initial potential energy. That's 30m plus 300. Now let's calculate our U final. Our U final is going to be mass times 10, this is the bucket, times 1. And our height is 1 because the box is 2 meters from the pivot point, and then the pivot point is 3 meters off the ground. So the distance between the box and the ground would be 1 meter. Plus 10, our mass of the projectile times gravity, and then that's 15 feet above. So that equals 10m plus 1500. All right, now let's figure out our K. Well, of the projectile, 1/2 mass of 10 times v squared. And then we have to add that to the kinetic energy of the bucket, 1/2 m v squared. Well, now we have an equation, and we can solve for v. So we could set it up. We know our U initial, 30m plus 300, and then that equals 10m 1500 plus 5v squared plus m over 2v squared. Let's erase this. Now let's solve for v. That's what it asks us to do. Well, we find equals, we could factor for v, 5 plus, okay, figure out v squared. That would be v squared equals m over 2, and then we're just going to take the square root of that. So to find our v, so that's going to be our formula for velocity of the projectile as it leaves the cup. Okay, let's write that down because we're going to need that. Write it down. All right. Now, complete the theoretical model by writing the relationship for x as a function of the counterweight mass using the results from B1 and B3. Oh, okay. So here, we calculated earlier that our time was 1.73 seconds, and we're given this formula, and we just calculated our velocity. So we could find that our x is 1.73 seconds times our formula, which is that of our formula of v, which is that 20m minus 1200 over 5 plus half of m. Well, that's pretty easy, right? All right, well, we just have one more part to do. And that is to just plug in a mass of 300 into this equation we just got. So this is calculator heavy, but I'm just gonna write out to do 20 times 300 minus 1200 over 5 plus 150. Okay, well, I'm going to get my calculator out, and I'm going to figure out what that is. So 20 times 300, that's 6,000, minus 1,200, 4,800, and then divided by 155, 30.97. So it's going to be 1.73 times the square root, 30.97. Okay. And so then our answer is going to be 9.63. Okay. So then it asks, give a reason for the difference between the theoretical value and the experimental value of X for the counterweight bucket of mass 300. Well, we got meters. Well, we got 9.63, and then our experimental value was for 300 is 37. So 9.63 versus 37. Give a reason for that. Well, it actually should not be that large. So we may have made a mistake in our calculation somewhere. I went over it a few times because I do them before. I'm not sure where I went wrong, but well, we can offer a logical explanation aside from just some actual physics mistakes. Well, we could offer a few reasons. We could say the masses we neglect because we neglect the mass of the rotating arm. We neglect the mass of the catapult. We neglect some masses and we don't really account for them. So we could, and in reality they do have masses. So we could say that causes a reason for the discrepancy. We could also say there's some air resistance in the real world. We don't account for air resistance in this problem. And then there would also probably be some friction on this figure 1 and that we don't account for. So all this stuff, in theory, it's much easier just to say it's negligible, but in the real world, it's really not. So, yeah. And that's FRQ number 2. Thank you.